Hello, and today we're going to talk about the Kelvin scale, or otherwise known as the thermodynamic scale. And we're going to talk about why it's different from a Celsius scale, for example. Now, what's special about the Kelvin scale is that it has one of its fixed points at an absolute zero. What does that mean? Well, first of all, fixed points. So, for example, the Celsius scale, we know that ice melts at 0 degrees Celsius, and then water boils at 100 degrees Celsius, and that's basically how they decided to make the Celsius scale, which is that they put that ice melting, that point should be 0, and then this should be 100, and we're going to divide every single temperature between these 2 points into 100 divisions. And that's how they came up with the Celsius scale. So the significant point at which something is a significant value is called a fixed point. And for the Celsius scale, it's these two big parts of water. And for the Kelvin scale, it is at an absolute zero. And what an absolute zero is it is a temperature at which all substances have the minimum internal energy. It is impossible to remove any more energy from an object at absolute zero. So in order to understand what constitutes internal energy, which is basically kinetic as well as potential energy, I highly suggest you watch my previous video explaining what internal energy is. But basically this means that when an internal energy is zero, kinetic energy is zero. The molecules will stop moving, and the potential energy is at a minimum. So let's take a look at what that might mean. Let's say we have a substance here that has molecules very tightly packed together, and this substance is at an absolute zero, which means that the minimum point that kinetic energy can be is 0. Can't be negative, which means that they stop moving completely. The potential energy is at a minimum. So you might have already known that these two molecules, they have electrical potential energies that is basically exerted on each other as due to their chemical bonding and stuff. So basically, they have a molecular or electrostatic potential energy. Now, if you do work and put them as far away from each other as possible so that these molecules are actually at an infinite distance apart, that's when its energy, this potential energy, equals 0. When you put them back together, the potential energy is going to decrease and it's going to be a negative value. So as long as they're not infinitely apart from each other, they exert completely no force on each other. As long as they're in each other's fields, they have a negative potential energy. And what happens at internal energy zero thing, minimum thing, is that this potential energy becomes the lowest negative number that it can possibly become. They're basically touching each other. They can't possibly become more close to each other anymore. And that's when they have the most negative potential energy. And that's when potential energy is at a minimum. So we've learned about that. Now, the absolute zero thing is really quite spectacular because molecules will just stop moving, and that means that it is the lowest temperature that is possible for every single substance. For every single substance, it can't be even colder than 0 kelvins, which is what one of their fixed points is, right? So absolute zero is 0 kelvins. It can't get colder than that. And that's why I think it's so special. For example, you might have heard of superconductivity. When a certain metal wire is in absolute zero, let's say it's connected to a battery and it is at absolute zero, it can run forever. And let's say we have a lamp here. It can run forever and it does not need to recharge its batteries or whatever. And why is that so? It's because within the wire, and let's say this is the wire, there are electrons that are moving and they're constantly being banged around. They're going like not in a straight line, but more in this sort of like squiggly crazy line because they're constantly colliding. What are these electrons colliding with? Well, they're colliding with the molecules of the metal, and the metal molecules are vibrating about a fixed position. And because they're vibrating, the electrons sometimes get knocked out of their way. Now, if all of these molecules were to stop moving and they were to have zero kinetic energy, the electrons could have a straight path without ever banging into one of the molecules, which means that they don't do work, they don't lose energy in banging into them and creating friction and then moving on. They can just go forever, and because the electric field created by the battery will stay, it doesn't actually need to give the electrons any extra energy to get through the wire, which means that electricity can flow forever. And that's why it's so special. At 0 kelvins, some crazy things happen, and one of them is superconductivity. So now moving on to the more practical stuff. Absolute zero that we just talked about, where all objects, all molecules stop moving, is negative 273.15 degrees Celsius in the Celsius scale, which means that, temperature at the Celsius scale, it's denoted by theta. Kelvin or thermodynamic scale is denoted by T. I think that's also pretty important to note. We can have a bit of a comparison here, where in the freezing point of water, where water turns to ice, in the thermometers, in the Celsius scale, we would say that is 0 degrees Celsius. And in the point where all of the molecules stop moving at absolute zero, we call that 0 kelvins. Now, 0 kelvins is negative 273 degrees Celsius. And in the same way, 0 degrees Celsius is negative 273 kelvins. So that's the difference, and as you can see, the divisions are the same. So let's take a look at some conversions. As long as you have this in mind, conversions should be extremely easy. So theta, which is the Celsius scale, is going to be the thermodynamic or the Kelvin scale temperature. You just minus 273.15 degrees Celsius, and you do that for the Kelvin scale as well. So the Kelvin scale is the Celsius scale plus 273.15 kelvins, and that's just how it works. For example, let's say some water is at 1 degrees Celsius. In the Kelvin scale, it's going to be, just use this formula right here, it's going to be 274.15 kelvins. As you can very much tell, it's obviously just going to be here. 1 degree Celsius is going to be 274. So this is pretty much common sense, and as long as you have this and understand it, this is strictly unnecessary. We can also round off the conversion factor to 273, so you don't have to put this 15. So here's a more easier depiction of how the thermodynamic scale compares to the Celsius scale. So as we've already said before, the freezing point of water, this is where ice forms, is going to be at 0 degrees Celsius. And when all of the matter stop moving, and that's when superconductivity can happen, we call that 0 kelvins. Now the difference between that is going to be negative 273, that's going to be 273 kelvins. So you might have realized that the difference between these 2 points, 273 K as well as 273 degrees Celsius, that's the difference, which means that the divisions of the two temperature scales are equal to each other. And that is actually extremely handy for us because it makes calculations really easy. All you need to do is subtract or minus 273. Whereas for other things, for example, the Fahrenheit scale, one division, 1 Fahrenheit is much smaller than 1 degree Celsius. However, the difference is the same for 1 Kelvin. So 1 Fahrenheit. 1 Fahrenheit is, I guess, almost half as small as 1 degree Celsius in order of the divisions. So you have to do a lot of multiplication in order to get conversions between the Fahrenheit scales and the other scales. However, for Celsius and Kelvin, it is the same division, which makes things very easy. So we can do a little bit of comparisons of the Celsius scale as well as the Kelvin scale. So a downside of the Celsius scale is that it is measured with a liquid in glass thermometer. Expansions may be nonlinear and only match at fixed points. What this means is because we kind of measure the Celsius scale using a liquid, which is water, we can also see that we usually use thermometers. For example, this mercury in glass thermometer, or this alcohol in glass thermometer. And what happens is basically when this liquid column, when it's at here, let's say at that point it's 0 degrees Celsius, so we say, oh, this point is 0 degrees Celsius, and then at 100 degrees Celsius this column would reach maybe this height, and that we would say it's 100 degrees Celsius. Now even if we put that there, it doesn't mean that exactly at half of these 2 points the exact temperature of this liquid would be 50 degrees Celsius. It might actually expand more when it's at a colder temperature, and then expand more slowly when it's at a hotter temperature, or vice versa. So the expansion rate in terms of the increase of temperature is not fixed, it's not linear. However, on the other hand, we have the Kelvin scale. Now, the Kelvin scale is an absolute scale, which means a ratio scale in which the unit of measurement is fixed and values are obtained by counting, which means that you have a fixed scale, unit, which is 1K, and then you basically just go up from 0K and you go up and up, so it makes things linear. We also look at it in terms of kinetic energy. The average kinetic energy is the same for all substances at a particular thermodynamic temperature. This is telling us that at 0K, which is a particular thermodynamic temperature, the average kinetic energy of all of the substances is going to be 0 joules. At 1K, it's also going to be x joules, the average kinetic energy, and it's going to be the same across every single substance, which makes it very linear and easy to measure and also to compare. So finally, I want to talk a little bit more about the fixed points of the thermodynamic scale. So as we've already talked about, the fixed points, one of them is absolute zero, and it's also defined as 0 kelvins. The other point is the triple point of water, and this is the point where ice, water, and water vapor can coexist, which can be defined as 0.01 degrees Celsius or 273.16 K. And at 0.01 degrees Celsius, let's explain that. So at 0 degrees Celsius, we know that water can be both ice and water. And when it becomes a little bit higher, 0.01 degrees Celsius, you can still have some ice there. You can still have some water, but because you have a little bit of extra temperature, you can still have some molecules that have enough energy to evaporate. So that's why we say that this is the triple point of water, ice, water, as well as some evaporated water vapor can coexist. Now, if you translate this directly into Kelvin scale, then that's going to be the temperature. So you basically take these two temperatures, 0 kelvins, triple point of water, and you divide it into 273.16 K. You get the same division as it is in the Celsius scale, and that's what we wrote here. The divisions of the thermodynamic scale are equal to that of the Celsius scale. And so that is about it for the thermodynamic scale / Kelvin scale. Hopefully it was very helpful, and I also highly suggest also taking a look at some other videos that I've also put up on physics, and thank you so much for watching.